Hello, ladies and gentlemen. I am Babalola. I am presenting the paper titled Detection of Bruder's Wheel Short Pulse Cause Using Time Domain Features with Hidden Markov Models, HMM. As we know that inshore Bruder's whales are one of the most endangered marine mammals in the world, it is therefore important to develop automated detection methods such as the HMM that precisely detects short pulse call produced by these whales in the presence of many other sounds. Hence, our objectives are as follows. Number one is to implement time domain features with the HMM for two things, detection and classification. The second objective is to determine the best time domain feature for the HMM. Before we proceed, I would like to discuss how our data was collected in this study. The data were collected using passive acoustic monitoring (PAM) within some days of January 2019. The data was recorded close to Gordons Bay Harbor and False Bay in South Africa, as you can see in the figure. That is the Google Map figure. We observed recommended minimum distance of 300 meters away from the animal before submerging our hydrophone in the sea. The collected data set consists of short pulse calls of inshore Bruder's whales along with dissimilar sounds, and our raw data was stored in an uncompressed and lossless format, that is a .wav file, to retain its original property. Thereafter, the collected data set was processed and annotated as follows. The first thing is to obtain a data set with less attenuation. This we did by filtering the raw data using MATLAB's bandpass filter in order to remove background noise and DC components. Here, we have selected passband frequency ranging between 90 Hz and 46,000 Hz. Since from study, the basic call frequency of Bruder's whale is generally greater than 90 Hz. Furthermore, the less attenuated sound which we have obtained is analyzed by visual and auditory inspection. Here we have used the sonic visualizer software as shown in the figure. This data set is then annotated as either the Bruder's whale snippet or any other sound, and in this case we refer to those sounds as the noise snippet. Now, I want to quickly describe the hidden Markov model, that is the HMM. The HMM is a stochastic process, that is a probabilistic process with non-observable underlying mechanism. What this means is that for a continuous signal like Haon, the HMM would do three things. It will train, it will decode, and will detect any given set of extracted vectors, as we have shown in our diagram. Okay? The training process involves estimating the maximum likelihood of the following parameters using the expectation maximization algorithm. The first parameter is the initial start probability, which we have referred to as pi. The second parameter is the transition probability matrix. This represents the probabilities of transiting from one state to another. And the third parameter is the emission distribution matrix. This matrix is associated with observation symbols. And in this case, we have mu, which is the mean, and sigma, which is the standard variation matrix. Then, during decoding, the most probable hidden state of the models is obtained using an algorithm known as the Viterbi algorithm. And subsequently, detection is performed on omega to determine whether or not the signal is received correctly. Sometimes the signal will not be received correctly. And we need to note that the performance of this HMM solely depends on the extracted features, which are typically determined during the detection process. Therefore, the focus of our study is to determine the best time domain feature vector to be used with the HMM. Okay? The feature extraction process can be performed in time or frequency domains. Take for instance, the male frequency substrate coefficients, MFCC, and linear predictive coefficients, LPC, are often used as frequency domain techniques with the HMM. But in this study, the feature extraction process is performed in the time domain, since Inshore-Bruder's wheel produces short pulse calls. These calls then have unique signal characteristics such as observable and limited call duration, mean, average power, and amplitude. Therefore, for each frame signal, we extracted three important time domain features, which are mean, average power, and zero crossing rate vectors. This is shown in the equation. These vectors were independently employed as feature vectors with respect to the frame duration and the number of states in the HMM. Now, to show our results, we simulate the performance of the HMM detector by varying the number of states and the frame duration using standard of measurements in the literature. We have used this sensitivity, we have used accuracy, and false positive rates. Table 1 shows the performance of the extracted features, which are average power, mean, and zero crossing rate, using different states, that is n equals to 3, 5, and 10, with a frame duration of 1 millisecond. The result shows that power is the most sensitive. As you can see, it's been highlighted in green. It's the most accurate and has the least false positive rate compared to mean and zero crossing rate. Using 10 states, that is n equals to 10 in the HMM, we could see that our results yielded the best performance using 10 states. Moreover, increasing the frame duration from 1 milliseconds to 5 and 10 milliseconds respectively, we could see in table 2 and 3 that the performance of the extracted features at states n equals to 3, 5, and 10 has shown that 1. Power is the most sensitive, it's most accurate, and yields the least false positive rate compared to mean and zero crossing rate. Also, using 10 states, that is n equals to 10 in the HMM, similar to what we had in using frame duration of 1 milliseconds, we also have that 10 states gives the best performance in the HMM. We can therefore conclude from our results that 1. The HMM exhibits best performances as the number of states increases with short frame duration. And secondly, we can conclude that average power as a time domain feature vector would yield the best performance and has yielded the best performance from our simulation compared to other feature vectors for detecting the short pulse score of inshore breeders' wheels based on the HMM technique. I thank you all for listening. I would like to know if anyone has any question. Thank you. You can also download some of our research work, and those are the things I've shown you there. Questions?